Today we are going to discuss mainly on two things. After understanding the electrode potential, Nernst equation, how those are calculated, we will shift our attention to this particular topic, electrochemical cells and Gibbs free energy. We have already discussed how electrode potential is related with equilibrium. And in this particular segment, we are going to understand that electrochemical cells are related to Gibbs free energy as well. So this is one thing. And thereafter, as we must have seen that in case of a Daniell cell, the zinc was gradually losing. The zinc electrode was gradually becomes thinner and the copper electrode was gradually becomes thicker. So on one side, the electrode will be losing its weight. On the other side, the electrode will be gaining its weight. So how much electrolyte is present, how much the dissociation will take place, at the same point of time on a particular electrode, how much it will become thicker with time and with how much of time, how much electricity will be passed through the circuit. All these things are going to be calculated over there. So two things, one is this one and next is the Faraday's law. So these two are the topics for today, and simultaneously we are going to discuss about its numericals also. So this is our topic. Now we know that in electrochemical cells the chemical energy is being converted to electrical energy. So what happens? The chemical energy this is being converted to electrical energy, and as a result of it, what happens? The cell potential is related to Gibbs free energy change. Remember, we have to prove that the cell potential is here related to the Gibbs free energy change. So in an electrochemical cell, the work done by transferring electrical energy through an external circuit, we are going to calculate how much work done is here. So electrical work done in 1 second is equal to the electrode potential multiplied by the total charge. So we can say that electrical work done in 1 second, electrical work done in 1 second is equal to electrical work done in 1 second is equal to the electrode potential multiplied by total charge passed. Electrode potential multiplied by total charge passed, like that. So at the same point of time, we also know that Gibbs free energy, the change in Gibbs free energy for a chemical reaction is the maximum useful work that can be obtained for the system. We simultaneously know this. So delta G is equal to maximum useful work. These two. Now, maximum work. Remember, for a reaction occurring in electrochemical cell whose electrodes differ by a potential of E cell, the work done when amount of electric charge Nf, small n into F, is passed along the potential of the cell is given by Nfe. Suppose there is n mole of n is the number of mole, which is the number of mole of electrons, and obviously we all know that 1 mole will carry 1 Faraday. The amount of charge, better I write, 1 mole carries how much of charge? 1 Faraday. So total charge carried by N mole is NF, right? And since the current is flowing through the external circuit, remember, current flows through external circuit. So that means by convention we take it as negative sign. It is by convention. IUPAC convention. So combining these three, as we have already said, that electrical work done in 1 second is equal to the electrode potential into total charge. Now total charge we have calculated NF, and electrode potential we designate by what? E0 cell, right? And there is a negative sign convention. So combining all this, we should be able to write delta G will be equal to minus NF E cell. And this equation is very, very important, because here we are calculating the maximum useful work that can be obtained from the system, which is, how do we calculate? It is the electrode potential into total charge. Now total charge, how much is passed? If the number of mole is N and 1 mole contains 1 Faraday, the N mole will contain N Faraday. So we are multiplying that with E cell, it should be E0 cell. So this formula will be very, very handy, and at the same point of time I would like to include, along with this particular formula, that if I erase, along with this formula only, we already know the delta G0 is equal to minus RT ln K. From the equilibrium chapter already we have seen that. And we have already, now we have seen that delta G is equal to minus NF E0. We also know that E0 is equal to, we have just seen that it is 2.303 by NF RT log Kc. So if I put this value here only, I will be getting delta G0 is equal to minus NF, it is into 2.303 by NF RT log Kc. As a result of it, we should be cancelling these out, and it remains as minus 2.303 RT log Kc. If you take it as this one. Now we know that if it is multiplied by 2.303, log can be converted to ln. So we can also say it is minus RT ln K delta G0. And we can say that ln K is equal to minus delta G0 by RT. So K should be is equal to e to the power minus delta G0 by RT, like that. So this is how the relationship is being drawn, and accordingly numericals will be solved. Do write it down, practice it. I think here we have correlated what is the physical significance. See, the equilibrium constant is actually related with the Gibbs free energy with this equation, from this equation also. This is also important. And if we know the value of temperature and the K of R is already known, we can calculate delta G0. So Gibbs free energy in this way is correlated with not only with electrode potential but with equilibrium constant also. So all these are correlated now. We will see one or two problems and then we will understand how the numericals will be solved. Now let us solve some related problems. So let me write down the problem first, then we are going to solve it. You also write it down. Question is, calculate delta G0 for the reaction. The reaction is given as Mg solid plus CO2 plus aqueous giving rise to Mg2 plus, which is aqueous, plus copper solid. Given values are E0 is equal to 2.71 volt and F is equal to 96,500 coulomb. So how to solve this type of problems? We have already gone through the formula. The formula is delta G0 is equal to minus NFE. So based on that formula only it can be solved. So you see E0 value is given, F is also given, and we need to calculate only the value of N. From here it is easily visible that Mg is giving rise to Mg2 plus. So the N value should be 2. Faraday is given, E0 is given, so directly put the values. It is minus 2 into 96,500 into 2.71. So here it is, you must remember that if I write along with the units, it should be like 2.71 volt. And this 96,500 actually is, better we write coulomb per mole into this, or you can say coulomb into mole inverse. So we all know that 1 coulomb volt is equal to joule, 1 joule actually. So coulomb and volt will combine to form joule. So it will be joule per mole. You calculate this numerical part only. As per the calculation of mine, I have done that with the calculator directly. It is coming as 523030 minus 523030. This is the value that I am getting, but you should calculate. It is by joule per mole. Joule per mole. So it is minus, you can say minus 523.03 kilojoule per mole. Very, very simple problem, but we have started with a comparatively easy one. Next question is, the zinc oblique silver oxide cell is used in hearing aids. Well, that's a new information, and electric watches. This equation is given, zinc giving rise to Zn2 plus 2 electron, that is been given already, and it is also given that Ag2O plus H2O plus 2 electron giving rise to 2Ag plus 2OH minus. E0 values are given, which is 0.76 volt for this reaction, and for this reaction E0 value is 0.34 volt. Question is, which is oxidized and which is reduced? First question. Which is oxidized and which is reduced is the first. The second question is, find E0 of the cell and delta G0 in joules. So this is the question. Now let us reanalyze the question. As per the analyzation, you can see it is very easy to guess that here what is happening, zinc is oxidized and the silver is reduced, because here it is 2Ag plus 2 electron giving rise to 2Ag, which is very easily determined, and zinc is obviously oxidized. So I think this answer is that zinc will be oxidized and silver is reduced. It's not a difficult one at all. We all understand, I think, what is happening here. Most important is the second part. Silver means you can say Ag2O actually is reduced. But the second part, we have to calculate E0 of cell. What is the formula of E0 of cell? E0 of cell is equal to E0R minus E0L, right? E0R means we are basically thinking about the silver cathode will be formed by this part. So E0 of, so it will be done by E0 of Ag plus by Ag minus E0 of Zn2 plus by Zn. As a result of it, this value is already given, is 0.34 minus, and it is also given, this is 0.76. I think, as per my knowledge, I think the E0 value of zinc is mistakenly given as 0.76. I think it should be minus 0.76. You check the electrochemical series, you will get the correct answer. So here it is minus 0.76 because it is below hydrogen, so there should be minus. Okay. Anyway, so this is volt. So how much we are getting? It is 1.10 volt. So we are getting 1.10 volt. This is the E0 of cell. Now we have to calculate delta G0 in joules. So delta G0 is equal to minus NF E0. N, obviously 2 electrons are being transferred. It is 96,500 coulomb, and E0 is 1.10 volt. Coulomb per mole actually. Coulomb per mole into 1.10 volt. Multiply to see how much you are getting. I am getting 21307. 21307 2 coulomb volt. This much I am getting, as we already mentioned that these two values, that coulomb into volt will give rise to joules, and obviously this value we are getting as this much joule per mole. So this is the value that we are getting, and what we have understood is if the equation is given, we will just calculate the E0 from there. So E0 we are putting here, delta G0 we are getting minus NF E0. So this type of calculations are very, very important. Similar problems we are going to continue to solve. Let us see the next problem. Similar, write it down. So just take the screenshot and write it down. The next one. Question is, the delta G0 for Daniell cell has been found to be minus 212.3 kilojoule at 25 degrees Celsius. Calculate the equilibrium constant for the cell reaction. Cell reaction is this much is given. Calculate the equilibrium constant for the cell reaction. So only this much is given. Cell reaction isn't mentioned. Let's see whether it is required or not. So delta G0 is already obtained, which is found to be minus 212.3 kilojoule. Now we know the formula, right? Delta G0 is equal to minus RT ln K. What are the values that we already have? R we know, T we know, delta G0 value is also given. So just straight away put the values. Delta G0 we are getting as minus 212.300. Let us put this value in joule. R, it is, we know the value of R, it is minus 8.314 joule per Kelvin per mole. Minus is there, 8.314 joule per Kelvin, and obviously per mole also. Then temperature, it is supposed to be 298 Kelvin. So these two are known. Now ln K into ln K. See, already these will be cancelled. You shouldn't be writing like that. You should calculate in your mind. Now if I try to calculate only ln K, ln K should be minus 212.300 joule divided by, here you see this one, minus 8.314 joule per Kelvin per mole into 298 Kelvin. This is the scenario. Now if we see the calculation, we know that K is a unitless quantity, it is the equilibrium constant. So from here we are getting, is like we are getting 85.69. as per my calculation. We are getting 85.69. That is ln Kc or K. So K, if we take the antilog, we will be getting 1.64. That we have already calculated and writing. Okay, 1.6 10 to the power 1.64 into 10 to the power 37. This part isn't important. We are taking antilogs only. The important is to understand this part. How are we calculating? Let us switch for the next problem. So next problem goes like this. It will be slightly lengthier one. For cell Mg2 plus and Ag2 plus, Ag plus Ag. Calculate the equilibrium constant at 25 degrees Celsius. We have to calculate equilibrium constant at 25 degrees Celsius, and also the maximum work that can be obtained by operating the cell. Maximum work that can be obtained by operating the cell. Two values are given. E0 of Mg2 plus Mg, that we are getting as minus 2.37 volt, and E0 of Ag plus Ag is equal to 0.80 volt. Now let us see how it should be propagated. Let us first formulate the cell. It is out of these two, this value is lower, this is higher. So it should be cathode, higher reduction potential, so cathode, and this should be anode, right? So anode should be on the left hand side, so I should be writing Mg2 plus, which is already given, Ag plus Ag. No. Easily we can formulate the reaction also. Mg gives rise to Mg2 plus 2 electron, and 2Ag plus 2 electron giving rise to 2Ag. Final reaction, again very easy. Mg plus 2Ag plus giving rise to Mg2 plus 2Ag. Now we need to calculate the value of E0. E0 value is E0 of R minus E0L, which is nothing but E0 of this one. R means Ag plus Ag minus E0 of Mg2 plus Mg. As a result of it, we are getting 0.80 minus 2.37 volt. And if you add these two, we are getting 3.17 volt. So we have got E0 now. Next is to calculate the equilibrium constant, that means K. So for that, what we should be doing is, we already know that ln K is equal to Ne by 0.059. If you formulate it in terms of log, it should be how much? We have already seen it is Le. fell by 0.059 at 298 Kelvin. The values are already known. N is 2. This is 3.17 divided by 0.059. So this part we are getting 107.45. We are getting log K. So the value of K, if we want to calculate, we are getting, I have already, see these values, this is the main thing. Next K, we have to take the anti-log of that. And that value you can calculate from log table. So we are getting K is equal to, the value that I have is, I'm just rewriting 2.56 into 10 to the power 107. This is the value of equilibrium constant. And since this high value suggests that the equation will be completely shifting to the right hand side, this reaction is so spontaneous. Now the calculation of maximum work. To do that, we know the formula is delta G0 is equal to minus NF E0. The value of N is 2. Here it is. N value will be 2 into 96,500 into E0 value, that is 3.17. Units I will be just writing at the last. So we are getting, again you calculate this easily separately. I have done all my calculations in order to keep the video comparatively lesser time. So I am getting minus 611,800. Minus 611,800. You can cross check by yourself whether you are getting the same or not. This is, as you know, this is coulomb per mole, this one, and this is volt. So the answer that I will be getting is in terms of joule. So obviously it is minus 611 kilojoule. It is the delta G0, which is the maximum work that can be obtained. So likewise, we have calculated the maximum work and we have calculated the equilibrium constant. So we are into a new segment of this chapter. Remember, this is the third segment of this chapter. It is called electrolytic cells and electrolyte. What is the process? If suppose, if I note it down, if say electricity is passed, the electricity is passed through electrolytic solution. What will happen? We have seen the electrodes will become thicker. That we have seen. That means, carefully listen, whenever a quantity of electricity is passed through electrolytic solution, then the electrolytic solution undergoes a chemical change. And that chemical change makes the electrodes become thicker. That chemical change is basically due to the reason of the electrons that will be acquired by the cations of the electrolytes. So, electrolysis is a process of decomposition of electrolyte by the passage of electricity. So, electrolytes are getting decomposed. Electrolytes are getting decomposed on electrodes. How much? The amount. Whenever we calculate the amount, that is known as quantitative aspects of electrolytic behavior, or rather we can say the quantitative aspects of electrolysis. And to explain this part, Michael Faraday, in 1833-34 I think, he has given two laws. This is known as Faraday's laws. We are going to go through this. So next segment is Faraday's law of electrolysis. Faraday's law of electrolysis. There are two laws, as I have told you already, that he has performed a huge number of experiments during that time, 1833 and 34. And so it's a very ancient case actually, and he has given two laws. The first law is like this. First law, Faraday's first law, is the amount of any substance deposited or liberated at any electrode amount of any substance deposited or liberated at any electrode is directly proportional to the quantity of electricity passed. Is directly proportional to the quantity of electricity passed through the electrolytic solution. Obviously, through the electrolytic solution. So here, if we explain it mathematically, we should be able to say the quantity of electricity is passed. If we say the quantity of electricity passed, that we take as Q, and the amount of Q we are writing in red rather, and the amount of any substance deposited, if we are writing as W, they should be proportional to each other. So we should be able to write W proportional to Q. And to remove this, we can write W is equal to Z into Q. Now what is that Z? It is called the constant, and is obviously Z is constant, and it is known as electrochemical equivalent. So this is known as electrochemical equivalent. Let us understand what is Q. Q is the quantity of electricity is passed. Suppose I is the, if we define in a particular case that the current of I amperes is passing from t seconds. Suppose the current of I ampere is passing for t seconds. In that case, the total electricity that is passed should be Q is equal to I into T. So as a result, we should be able to write W is equal to Z into I into T, and this is the formula. Furthermore, interestingly, if we take that as 1 ampere, if we take that in 1 second, we should say W is equal to Z. Hence, from here only, if we need to define the electrochemical equivalent, we should say that electrochemical equivalent is the amount of substance deposited. The electrochemical equivalent of a substance may be defined as the mass of substance or amount of substance deposited when one current of 1 ampere is being passed for 1 second. One ampere of current is passed for 1 second. So here we have defined what is electrochemical equivalent from the Faraday's law. This is the main formula. We need to understand this one also, the total amount of current that is passed, electricity that is passed. So this is the Faraday's first law. Obviously numericals are there which we will be solving. Now let us pay our attention to the second law of Faraday. So you write it down, I will erase. It is the second law. As per this law, Faraday's second law suggests when the same quantity of electricity is passed through different electrolytic solution connected in series, the weight of the substance produced at the electrodes are directly proportional to their chemical equivalent weights. So it is when the same amount of electricity is passed through different electrolytic solutions connected, that is very important, connected in series. They must be connected, otherwise there is no point. Then the amount of substance deposited, then the amount of substance deposited at the particular electrodes are proportional to their chemical equivalent weights. So this is the Faraday's second law. Carefully see to it. Suppose, how to explain this law? Suppose there are two solutions, okay? Copper sulfate and silver nitrate. Suppose copper sulfate and silver nitrate, these two solutions are connected in series. These two are connected in series. In that case, according to this law, weight of copper deposited divided by weight of silver deposited should be is equal to, means this by that will be the ratio of their chemical equivalent weights. So it should be equal to equivalent weight of copper and equivalent weight of silver. And this is the formula that we are going to utilize. Now, we will see in the next class how the calculations of Faraday's law will be done. So whenever next we are having live interactions, again I am telling you, be prepared and come, because in live interactions I am going to ask the questions. What is Faraday's first law and second law? So whoever will not read will have problems. I expect you to read the Faraday's first law and second law and all the problems that we have discussed. Based on Faraday's first law and second law, we are going to solve problems on the next day. So read this carefully, practice it. I hope you have understood the two laws. Obviously, if we solve the numericals, it will become much more easy.